What up? How's it going? Hope everybody's doing well. All right, what we're going to be doing from now until basically the end of November, maybe towards the middle of December, is working a little bit on the projects I'm going to outline here, but mainly sharpening up the presentation that I have. So during a PhD, you reach a point where you do what's called a proposal. It's essentially like an oral exam, but um, what you do is basically outline what you are expecting to conduct, like the experiments you're expecting to conduct towards like the latter half of your PhD. So it's very big. Honestly, it's more important to pass this than it is that it's harder to pass this than to defend, is what a lot of people say, because they grill you on a lot of the basics and they ask you like they basically try to get you to say that you don't know the answer to a question, right? Um, so this is what I'm going to be doing for a while, and this also kind of might give you somewhat of a better background on like what we do here on stream. So um, regardless, we're going to be running through this PowerPoint a lot and thinking of potential questions that my committee will ask me. So this is the title. So I'd go through the introduction, like, "Hey, my name's Dominic." Da, 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 da. But this is the title of the work that I'm doing. So this basically encompasses two main projects. The first one being creating a model for predicting HDX-MS, which is an experimental technique that measures, um, in some sense, the dynamics of a protein. So I want to create a model for predicting that based upon protein structures. And then the second part would be generally just trying to understand and explain the catalysis of a RIP from Hallam 2 and hopefully use our predictive model to help us explain the enzymatic pathway of Hallam 2. So this is the presentation overview. We have a little bit of a theme going on. So each of these colors will be presented up here on the left so you can have an idea of like where we're at uh, progress-wise in the presentation. But initially I want to cover basically a motivation for why this work, why I'm doing this work in the first place. And then in doing so, I want to outline the state of the art and the limitations of that state of the art. And then I want to explain why HDX-MS is kind of what I believe to be the way towards addressing those limitations. So I'll explain what that is and why we should care. And then I'm going to talk about our approach to our model, which is called D2O, stands for Dynamics to Observation. I'll talk about the architecture, how we're validating it, and the applications. And then we will finally go into Hallam 2, which is kind of the second portion, the second big project of my PhD. And then we'll talk about a little bit about the background of Hallam 2, some of the observations I've made, and then going forward, what we're going to do to study this more. All right, so that was two slides. How long was that? I'm kind of curious. How long have we been going for? Those are like 4 minutes. Really, the presentation should be about an hour long. I should be timing myself, but it's fine. All right, so just to start, I want to talk about AlphaFold. Hey, Parakeet, how's it going? Yeah, this is the probably the biggest presentation I'll make in my PhD besides my thesis, really. And besides my defense, I mean. So we're going to be seeing a lot of presentation. But it's fine. This gives viewers like a bit of a background. Oh, I don't know. I'm at 63 right now. But hopefully I'll spend less than like a minute on each of these. Rise and grind. I like waking up early because I feel like I can kind of shit around midday, like after lunch, like take a little siesta. Um, anyway, so initially I want to talk about AlphaFold. So it goes without saying that AlphaFold has changed how we approach answering scientific questions. As you can see from this graph here, we have greatly expanded the number of candidate structures for proteins. In fact, in 2022, we have defined the structure for all known proteins, which is pretty remarkable. So this gives researchers the capacity to probe the space of protein structures for any ideas regarding the nature of their shape and function. Um, that said, this tool, extensions of this tool can be used for preliminary screening and validation. Talking about the grandma hosting and music, making competition with 19 strangers someday. Yeah, it's exciting. Let me know how that goes. So yeah, so AlphaFold, really like kind of like the most direct extension of that program is for preliminary screening and validation. For example, in just like a few clicks, you can see how changes to a protein sequence influence is the model's prediction. So say like for example, if you were to do this across homologs, you could potentially derive like cross comparisons in 3D space, which is pretty useful. Yeah, this is kind of like the most like I think this is the graph that summarizes how important AlphaFold was basically. It really was. It is like a revolution in biochemistry. Um, but I'm going to talk about the limitations though, in a second. So yeah, one of the main use cases for AlphaFold would be to look at mutagenesis. So like if you predict a structure and you have like homologs per se, and you predict those structures, you can actually see, you can cross compare those structures and then um, look at like analogous residues within 3D space. So this gives you like another depth of um, knowledge that you wouldn't necessarily get with just like multiple sequence alignment. Um, so in another case, like what AlphaFold might be used for, so you could actually seed different predictions and modify temperatures so that you might can understand somewhat what the dynamics of a protein is if the predictions are different from each other, and those differences may actually be representative of the conformational landscape of a protein. So naturally, with these use cases, the number of citations for AlphaFold has pretty much exploded. As you can see here in this graph, it's just gone up and up. But AlphaFold, of course, is not without its limitations. I want to emphasize that much of AlphaFold's uses are preliminary. So given like the complexities of a protein, there are many things that simply are not captured in the training data for AlphaFold. For example, like the main question here with mutagenesis is, does the confidence of predictions correlate to any real effect a substitution may have? Surely there's some overlap, but the effects of mutagenesis likely pan out in the dynamics rather than in, say, a static structure. So another question you could ask is like, how many solved mutant structures are there really? And of those, how many lead to significant changes in their conformation, right? Likely a lot of the effects of substitutions play out in the dynamics rather than a single structure. And regarding dynamics, like the core question here is like, how much of the conformational space can we cover with just repeated predictions with different temperatures and starting seeds? So there's actually some like pretty interesting work that dives into this a bit. And it seems like it can be done with some hacking. This, of course, really is limited to proteins that have already a deep MSA sources, and obviously you need expertise with AlphaFold to be able to do this in the correct manner. So, and this is all to say that we're kind of like a bit a ways from like exploring the conformational landscape of a protein with just like a predictive model like AlphaFold. So it's just me and my committee members. So it'd be me like presenting to like 4 professors basically. God, why does this take so long? So slow. Yeah. Thank you. It'll get worse, don't worry. But kind of like the key thing that I want to do while I'm going over this presentation is think about questions that they could ask. Like kind of the first one that I thought of is like right here. So anytime you mention like a paper, they have free reign to basically ask you like what that paper is, right? So I'm coming up with like a list of questions. So like on slide 11, you mentioned a paper. What is it? So I need to remember. I need to pretty much have like a 1 sentence candid statement about like what this paper is. So and then maybe some potential questions that they would ask from that statement. So I need to go deep basically. But so this paper is actually pretty interesting. So some researchers at Brown took AlphaFold 2, and they showed that they can directly predict the relative populations of different protein conformations by subsampling multiple sequence alignments. So the way how like AlphaFold works, basically it takes in data regarding like the evolution of a protein. We have someone actually learn from your presentation right now. What do you mean? Yeah, you can ask questions because I need to what is it, like practice answering those. Oh yeah. hmm I see what you're saying. Yeah. This is like really good practice for me, you know. Um, so like yeah, so the paper basically the way AlphaFold works is, um, and this is like a very crude, like broad brushstrokes, like what how AlphaFold works, but basically you have a protein that has been solved with say like X-ray crystallography, and this protein has a evolutionary history through like the protein sequences that are like through homologs, right? And from that, you can pick up on patterns where, like, say, mutations occur in evolution. Um, but for the most part, AlphaFold picks up on what are the like consistent things that come across that evolutionary thread, and it uses that to predict ultimately like a ground state structure for a protein. So um, AlphaFold tends to pretty much predict like the same sort of structure, even across homologs, they're going to be quite the same. So what they did was basically tweak the MSA, which is that evolutionary tree, so that it was more shallow, and then they added what's called dropout to the layers. So this is basically like you can think of like in your brain, like imagine like turning off some neuronal pathways, like just like 10% of them, like you would kind of be quite different than what you would normally be with all your brain normal patterns firing. So that's what they did to the model for AlphaFold. And from there, they actually got some different conformers that look as though they were representative of the conformational ensemble. So that's what they did to basically get AlphaFold to predict different different protein structures. Are there ever any defects coming from evolution mutation proteins? So yeah, but you almost wouldn't even see it because if there are defects, then that organism is likely not going to pass their genes on or reproduce, you know. So a lot of what you see in nature is has been optimized from like, you know, millions, billions of years. Now you can honestly say that like, you know, a mutation or like a defect, like these things are like random. So really you can have like a good defect or a bad defect, you know. You know. So just what you typically like the proteins that are kind of ubiquitous in organisms are ones that were created to have or at least are just good for the organism basically. It helps them survive, you know. But so that would be like the first question. I think they would ask us maybe something about this paper and explaining this. And that would kind of lead to like an AlphaFold explanation. So on some level, like I need to at least because like we're only on slide 11, right? Like I need to kind of cap like the level of depth that I go into these things because I want to get through like a presentation, you know. So it's kind of hard to figure out how deep I need to go, right? They might ask me how AlphaFold works. All right. So um, all this is to say, clearly it's not enough just to use AlphaFold yet. In fact, I would venture to say that the most of the scientific community just uses the software to generate pretty pictures of their protein. So I probably should remove this because it's kind of bashing AlphaFold, I think, a little bit too much, even though I think it's true. But so I guess I'll just say clearly it's not enough to just use AlphaFold yet. To get something concrete, we need to collect more data that is interpretable, rigorous, and experimentally valid. When are you presenting this? Either the beginning of December or mid-December, if they get back to me on their availability. Thank you. Yeah, so we need to collect more data that is interpretable, rigorous, and experimentally valid. So on the computational side of things, there is MD. So this is like a routine way to get dynamical information at the atomic level. So here they might stop me and ask me like, okay, what's molecular dynamics? All right. Um, so molecular dynamics is basically a strategy that uses classical assumptions to model the motion of atoms. Okay, then they might ask me, what are those classical assumptions, right? So, um, and what makes it like a classical assumption? So basically, like with an atom, they contain electrons, right? So in MD, we don't consider the motion of electrons and their interactions. Another thing is in MD, a part of an atom does not change its charge in response to its local environment, whereas in QM that would be the case. Um, and um, the motion of which these atoms partake in are governed by Newton's equations. Okay, so they might ask me, okay, what are the equations that govern MD? Right. So this is kind of I did this yesterday. So like we would first start with force equals mass times acceleration. So the force is the negative gradient of the potential. And so to calculate potential, you would basically use equations for bonded and non-bonded interactions. So this would be like for the bonded, for instance, it would be like the bond stretching, you know, or the dihedral angle. What would be another one? There's a couple more. Yeah, bond stretching, bond angle, dihedral angle. This is just those three. Bending. Bond stretching, bond angle, and dihedral. I think that's enough. So those would be like the bonded terms. And then the non-bonded terms would be like these electrostatic interactions and Lennard-Jones potentials. Okay, van der Waals and yeah. So the van der Waals are often modeled by the Lennard-Jones potential. Okay. And then electrostatics. Right. And yeah, so they might ask me like, okay, so whenever you use those equations, how do they scale? So it'd be quadratically, it'd be O to the n squared. But this is kind of lowered actually because with say like these non-bonded interactions, you would invoke like a cutoff and approximate things, you know. Like the interactions would kind of fall off after a certain distance too. Um, so now, honestly, that'd probably be enough, but they might ask me like, okay, let's talk about these equations, right? And this is where like I kind of really need to like dive in a little bit more. But I say that we would first start with F equals ma. So there's like the Newtonian equation for force. Let's look that up. So it would be first law. Would it be second law? Yeah. So it would be Newton's second law. What? So you're taking, I think you're taking Chem 1, right? You would kind of get into this maybe with like physical chemistry or physics, really. So this is like, this is something that you learn in physics class. Yeah. So a lot of the, well, basically the equations that govern these MD simulations are Newtonian equations. So it'd be Newton's second law, F equals ma. So the force here is, we calculate it as the negative gradient of the potential. So so we could derive that, because force equals mass times acceleration. So we're basically trying to figure out like where to apply the force so that the potential energy is minimized. Well, if you have any questions, then feel free to ask me. I tutor chemistry all the time. Yeah, I mean, honestly, I'd hope so, because if I wasn't, then I shouldn't be in a PhD program. Um, Thank you, though. But so in MD, you're trying to basically move these atoms such that the potential energy is going down, right? So what you would do is take the negative gradient of the potential, which is essentially like partial derivatives along each coordinate, right? So for example, like in like a 1D harmonic spring, the potential energy of the particle can be modeled as 1/2 kx squared. So if you take the derivative and apply the negative, you get negative kx. And from there, you can compute the acceleration of the particle. Oh, okay. Yes. What's that called? Um, Stoichiometry. So I was gonna look. So I asked ChatGPT, kind of gave me a pretty good summary of this stuff. All right. So this is taking a ridiculous amount of time. So what I'm gonna do is yeah, it's very helpful. It's just a better Google, really. Did I not accept it? Do it? What? So is there something going on then? Narvel is healthy. So what's going on then? That's good. I think so. It's unfortunate. Like some teachers are like becoming real Luddites about AI, and like it's not going anywhere, and it's only going to get better. So I think teachers need to start learning how to like integrate it into their workflow, and teach students how to use it rather than you need to start elevating the requirements of students at this point. You know, AI should free your mind to think of more complex things rather than do like answer like stupid questions, right? Yeah, well, I mean, it's not good. It's not super intelligent right now, right? So it's not going to do like right now. It can't do like most of the work that I do. You know, it can help me understand things, right? And but ultimately, I have to tell it, what to do. All right. Do you get to choose a side, or do they assign you one? All right. So what was I going to do? Empty force field description. I don't know if it was this one. Oh, I think it was this. Right. So this is F equals ma right here. Um, and then so negative potential energy. So to find potential, so what is the equation for potential energy? PE equals, so that's for a spring. Can we do that? The equation for potential energy is given a conservative force. Okay, yeah. In one dimension, the force is the negative derivative of the potential energy. It's kind of interesting how that works out. Yeah, formulas are sick. Um, oh, I remember reading this in physics class. I just really have to dumb it down for myself. That was the one thing. If a force acting on an object is a function of position only, it is said to be a conservative force. If a force acting on an object is a function of position only, it is said to be a conservative force. And it can be represented by the potential energy function, which for a one-dimensional case satisfies the derivative condition. I'm almost there. So I think it has something to do with like the equal and opposite thing. Okay. Force is the negative gradient in one dimension. This means that the force acts in a direction that is the steepest decrease in potential energy. Why does force act in the direction of steepest potential? Because it is the natural tendency of a system to minimize its energy, and this minimum energy state is reached by moving along the steepest. It's a scalar, but it has no direction, but it contains directional information through its derivatives. Forces is a vector operator that points in a direction of the steep greatest rate of increase of the function. Work and energy. A conservative force does positive work on an object as it moves in the same direction as the force. Yeah, I am learning literally day one physics. There's no way. um, right, so this is just a relationship here. Okay, and the reason why this is the case is because um, a ball rolling down the hill. So the force that will be applied to the ball will be the negative gradient of the potential energy. So equal and opposite. Is it equal? All right. So in a 1D harmonic potential has that. So the force is this. So I guess this is saying like depending on, because the potential energy depends on the position x, you know? And so you can calculate potential energy at a position, so that's just a scalar. So the force acting on the object in that position will be this here. So I don't understand how this gives you the direction though. Like this just gives you the force acting on X. I don't think it does give you the direction. So yeah, this will be the force at these dummy numbers. You can solve for acceleration by rearranging the F equals ma equation. So the atom is being pulled back to the origin with acceleration -2. Okay. So the force is -4, and the acceleration would be -2. Okay, so this is where things get a little bit complicated with the Verlet algorithm. So this is how we update the position here. So we recompute the force at the new position to get a new acceleration. Okay. So update position, right? So this is the equation here. So if the original position is the original velocity. Also, we already have a velocity set in the beginning. Delta t is the change, that's the time step. Okay. Plus 1/2 et delta t squared. So what do all these numbers mean though? Like exactly. I know this is velocity. So it's the speed as going initially. And what direction though? I guess it'd be along positive x. Like, yeah, you should take a physics class. Just for like, not even job sake, just for like for your own sake, you know. Jobs will come. Don't even worry about that. You just wanna pick something you enjoy doing, really. You know, you want to pick something you enjoy doing, and you want to be useful. That's really it. Then you'll succeed. So do something that's useful to other people, and do something you like to do. Um, is okay, right. So these signs here imply a direction then. Okay. So why is the time step squared here? Like, where does this equation come from? See, am I getting too deep in the weeds right now? Yeah, I think that'll be a very fulfilling career, a teacher. Yeah, I knew that. I wish governments would subsidize like people with PhDs to teach in middle schools and high schools. Like, I think that would solve a lot of society's problems if that was like written into law, you know? Because I would do that if I got paid like, you know, 80K a year. Yeah, no, but if the government subsidized it, like, what does the government spend money on? You know, they could spend money on that. They could do that. Just have 10 less bullets for every gun. It's frequently used to calculate trajectories in molecular dynamics, computer graphics. The algorithm was used in 1971. Wow. Has been rediscovered many times since then. Oh, loop of Verlet. What dog? Yeah. Education's going down the can here. We're focused on other things, like Venezuela. Orbit of his comments. Provides good numerical stability as well as other properties are important for time reversibility, preservation is symplectic form, phase space, over the, over the simple Euler method. After transforming to bring the masses, I'm forgetting. The equation can be simplified to that, representing the position-dependent acceleration. Typically, the initial position. I think we need to watch a video. There's got to be a video on here. That's funny. Really? Well, our histories are kind of intertwined a little bit.
Hello. In this video, I'm going to tell you about the velocity-Verlet algorithm, and I'm hopefully going to give you all the information you will need to start writing your first molecular dynamics code. Before I get onto that though, let's just try to take a moment to understand why molecular dynamics is used in statistical mechanics. In the first assignment for this module, you learned how to calculate ensemble averages by explicit enumeration. I taught you how to calculate these ensemble averages when the temperature is
I don't even know what that is.
In this
Don't even
video,
ask me.
we're going to consider how you calculate the ensemble average when the energy is fixed. But the method is similar to what you did to calculate the ensemble averages when the temperature is fixed. In actual fact, it is probably easier to calculate these ensemble averages when the energy is fixed. So, without further preamble, allow me to explain the meaning of the symbol on the slide. The A in angle brackets here means the average energy of the quantity A for a system with an energy of E. To be clear, A here could be any property that interests us. For example, it might be the magnetization, the volume, or even the microscopic coordinates of one of the particles in the system. The only requirement we have of A is that it must be possible to calculate this quantity for every microstate the system might adopt. The reason we need to be able to calculate A for each microstate is that the ensemble average is given by this expression. In this expression, the sums run over all the microstates the system can be in. AI is the value of the property A for the ith microstate. Lastly, the delta that appears in the numerator and denominator is a Kronecker delta, which is 1 if EI is equal to E and is 0 otherwise. This whole expression is thus just a fancy way of saying that the average value of the property A when the energy is E can be calculated by taking the n states that have an energy of E and adding together all their A values and then dividing this by n. Now, as you hopefully recognized after the end of the first exercise, the problem with using this expression is that for any modestly sized system, the number of microstates is enormous. We thus simply cannot explicitly enumerate all of them and check if they have an energy of E, as it would take far too long. We thus have to cheat and instead generate a small sample of the states with energy E and hope that the ratio that we get from this is approximately equal expected term name energy, as analytically these framed in the velocity Verlet algorithm using the expression shown on the slide here. The expression we are using here is the Subat equation V equals V by the mass of E plus delta, and that you can return.
All right. I think I come back to this. Maybe let's try one more.
If you drop a ball from 5 meters, how long does it take to hit the ground? This is one of my favorite questions to ask beginner programmers, because it has an analytical solution. Let's start with the kinematic equation. X equals x naught plus v naught t plus 1/2 at squared plus 1/6 bt cubed and higher order terms. If we assume that our initial velocity is 0, that no one cares about our b term because it's a jerk, our final position is 0, our initial position is 5, and that we have an acceleration that is roughly negative 10 meters per second squared, we can solve for t and find that it's roughly 1 second. Because of how straightforward this is, whenever I have a new algorithm to solve Newton's equations of motion, this is my favorite test case. That said, we don't really need anything special to figure out how long it takes for a ball to hit the ground when dropped under constant acceleration. However, what if our acceleration is no longer constant, but instead a function of position, which is a function of time? Imagine, for example, an asteroid moving through multiple planets' gravitational field. Well, in this case, we're going to have to rethink how we implement this in code. And here's where Verlet integration comes in. We want to find the trajectory of some object influenced by some force field. So we start with the object's position and try to find its new position one time step in the future. Obviously, this follows from the kinematic equation. The trick here is that we also take one time step back. In the time step back, we see that both the velocity and jerk terms are negative, which is incredibly important because when we add them together, these terms will cancel out, leaving us with an error term of delta t to the 4th. Which is pretty good, but what if we actually need that velocity for something, like maybe calculating the kinetic energy? Well, never fear, Stormer is here. He said that we could calculate the velocity of any object simply by taking its position one time step forward and its position one time step back, and dividing by 2 delta t. Which sounds great, except let's go back to the case of an asteroid moving through the gravitational field of multiple planets. Here, it's obvious that the initial velocity of the asteroid actually impacts its trajectory.
It's a train.
Don't worry, those crafty computational physicists thought of something for this too. It's called the velocity Verlet algorithm, where they basically said, screw it, we're just going to use the kinematic equation every time step. It's exactly what you think it would be. There's more information about the Verlet, Stormer Verlet, and velocity Verlet algorithms on the Arcane Algorithm Archive right now, so feel free to check it out. But here's where I drop the ball and you pick it up. So if you want to help out, feel free to write on the Arcane time step. It's...
That was a good video. Yeah, this train literally drives by at like 2 a.m. Essentially a solution to the kinetic equation for the objective motion of any object. For the motion of any object. So x naught, initial position, velocity at time t is 1/2 acceleration t squared. B is often forgotten jerk term, and t is time. This equation is essential equation for almost every Newtonian physics solver and brings up a class of algorithms known as force integrators. One of the first force integrators to work with is the Verlet integration. So let's say we want to solve for the next step, x, to a close approximation, actually performing a Taylor series expansion. It might look like this. Okay. I still don't get where this comes from. I get this because velocity is like distance over time, so we're basically calculating the distance here. But I guess we'd be calculating the distance over this. So units for, so meters per second squared. So it's canceling that out, but the 1/2. So here we're getting distance too. Where's the 1/2 come from? God, I forgot everything about this. afraid to look like an idiot. Um, where does the 1/2 come from? Okay. The factor of 1/2 comes from the fact that with constant acceleration, the velocity of an object is changing linearly over time. I get that. So you use the average velocity to find the distance. Velocity is not constant. Okay. Distance s is integral with respect to time. All right. So the distance s is the average velocity. Okay. 1/2 effectively accounts for the fact that the object spends its time traveling at speeds ranging from the initial velocity to the final velocity. So using the average velocity, which is halfway between the start and end velocities over the period, gives you the correct distance. I guess that makes sense, actually. All right. I'm there. Okay, so let's say we want to solve the next time step x. To a close approximation, actually performing a Taylor series expansion. This might look like delta t, okay. This means that if we need to find the next x, we need the current x, v, a, etc. However, because few people calculate the jerk term, our error is typically that. That said, we can calculate x with less knowledge and higher accuracy if we play a trick. Let's say we want to calculate x from the previous time step. Again, to a close approximation, that might look like this. So it's just the negative. Now we have two equations to solve for two different time steps x. One in which we already have. If we add the two equations together to solve x, we find that wait, what? So we're adding this plus, we're adding these two. 2xt I'm just going to take their word for it when you do the math or the algebra. So this means we can find our next x simply by knowing our current x and the x before that and the acceleration. No velocity is necessary. Which is great here, looks like in the code. Now, obviously, this poses a problem if we want to calculate a term that requires velocity, like the kinetic energy. In this case, we certainly cannot get rid of the velocity by using the Storm-Verlet method. We have equations for, so let's start there. If we subtract the latter from the formula, we get, if we solve for Vt, we get Now let's say we actually need the velocity calculator next time. So well, in this case, we simply cannot use the above approximation. Instead, we use the velocity Verlet algorithm. In some ways, this algorithm is even simpler than above. We can calculate everything like okay. All right, I think that's enough for looking into the Verlet algorithm. Because ultimately, like, we just want to answer, like, what is MD, you know? So what do we learn here? Yeah, what equations govern an MD update, you know? So force is the negative gradient of potential for a 1D harmonic spring. If you take the derivative, you get negative. So from there, you can compute acceleration of the particle. So in MD, you would normally apply the Verlet algorithm to update position. We can compute the force at the new position, then update the velocity. In real MD, you would do this, but for 3D vectors, the potential energy would then be a combination of bonded and non-bonded forces. So I think eventually I want to get to the point where, like, I fully comprehend this, where it's like back of my hand sort of knowledge. So maybe we don't have to do this now because we kind of just want to get through most of the presentation, I think, today. So all right, table that. But so with these, this addresses the limitations of AlphaFold essentially, because you can simulate atomic motions and you can get more of a variety of the effects of, say, like mutations or sampling different seeds during predictions, right? On the experimental side of things, we have a bunch of options here, but I will refrain from like explaining what each of these do and more so talk about their limitations directly. So for MD, really what mainly limits MD from being used as frequently as it should be is because of size constraints for the proteins. Also, like, if you don't have access to a supercomputer, it's kind of hard to run MD. So it's kind of computationally inaccessible for many people. Then also sampling, there really is kind of no tried and true method of getting rare yet functionally significant conformations. You kind of have to weasel your way around to get those. For X-ray crystallography, it's hard to do, and the outputs that you get from there are really non-native. They're in those are like packing effects. So is there any question? Like, would there be any questions they would ask me on X-ray? I don't think so. How does X-ray crystallography work? I don't think they'd ask me that. Maybe I could give like a brief sentence though, How does X-ray I want to go into this presentation knowing like everything, just about. From what I understand, X-ray crystallography works by basically you have a protein that you've crystallized. So what's a crystal? A crystal is just like a repeating periodic arrangement of protein structures. With that, you can shine X-rays at it and then get a diffraction pattern and then run a bunch of algorithms to get to solve basically the structure, three-dimensional structure of the diffraction pattern. And then directing a beam of X-rays at the crystal, the electrons in the crystal scatter the X-rays, creating a diffraction pattern. This pattern is then mathematically processed to generate an electron density map, and a 3D model is built from fitting atoms into the map. Yeah, okay. So I think I got that right. Creating a diffraction pattern of spots on the detector. The pattern is then mathematically processed to generate an electron density map, and a 3D model of atomic structure is built by fitting the atoms into the map. Okay. So they might ask me like, why is it hard? I don't know. I doubt it. What is cryo-EM? So here, I'm actually kind of happy I'm doing this because I don't really have like a solid knowledge. So cryo-EM, I think, is basically you have some concentration of protein in like solution, and you basically lay that on like a thin film, and this film is flash frozen with like some cryogenic liquid, like maybe I think it's like liquid hydrogen, and from there you basically freeze the protein in like whatever sort of native conformation it was in, and you use electron microscopy to gather what is like the two-dimensional picture of that protein. And then from there, you kind of just like, again, use an algorithm to determine like the three-dimensional structure. And you could actually get some dynamical information from that because the protein exists in a bunch of different conforms. So that's what my definition of cryo-EM is. Into an amorphous, oh yeah, vitreous ice. That's the term. I need to go to the bathroom with this. So cryo-EM, rapidly freezing biological samples into an amorphous ice-like state called vitreous ice to preserve their natural structure. So vitreous ice, I know, is it freezes so fast that the water molecules don't even arrange themselves. It's like this would be like a phase of ice or a phase of water. But vitreous ice is basically one where they don't have time to organize into crystals, I believe. Hmm. Yeah, non-crystalline glass-like form of water formed by extremely rapid cooling that prevents water molecules from forming a crystal lattice. All right. A transmission electron microscope then sends thousands of low-dose 2D images of the sample from many different angles. Powerful computer software then averages and reconstructs the images to create a high-resolution 3D model of the molecule. A transmission electron microscope. Don't even ask me. Uses a beam of electrons to image ultra-thin specimen and allowing for high resolution. So you can get like macromolecular structures. So I think it's better like the bigger the protein. Regardless, we're not going to dive into the weeds on that. I mean, if they ask me like how does a transmission electron microscope work, I'm just going to be like, I have no idea. I like this description here. But I think the key term is like vitreous ice. All right. So, and protein nuclear magnetic resonance. I've actually done something. I've done a presentation on this before. Do I remember? No. So regular NMR basically, um, so what it does, you dissolve something in like a protein in a solvent that is not affected by an external magnetic field, and then the molecule that is um, responsive to an external magnetic field will basically like move in a unique way such that you can determine what are its neighbors, and from that you can gather the structure. So it kind of predicts a spectra rather than like direct images. But it depends on basically like an external magnetic field. So let's see. Multi-dimensional experiments predict a picture. Okay, I think I got it right. So yeah, this would be like the spectra right here. I don't know how you get a structure from that though, honestly. So you could do 4D to 2D to 4D NMR. I wonder if you could do like PDB to NMR. Can you do that? I don't think you can do that. Can I convert a PDB to NMR spectra? No. Why not? There's no. So this is. I'm kind of getting distracted right now, but I think this is just them creating a data set. Yeah, this is cool actually. Zurich. This would be lit. That'd be a fun little project, like work on using this data set for predicting possibly dynamics even. 04 January 2024. I wonder who cited this. Sequential backbone. Why does it say 2026? Do they have like a GitHub or something? Well, to anyone out there who's interested in doing a project, I would definitely look into this probably. All right, so going back. So maybe they can tell me what protein NMR is. All NMR-based information is derived from these spectra generally. Despite the essential importance of NMR, these are so far not systematically archived in public database and therefore not readily available to other researchers. Although it does not support time domain, some standardized data sets are collected. The fact that NMR structural protein determination are in general hampers NMR studies. There's never enough data for any of this shit due to the lack of. Oh, so they already made a model. That's cool. Use ResNet, residual neural network, then a graph neural network. Looks like a black box model for the most part. Did it work? Predicted RMS data reference. So I'm RMSD like a below 2 is pretty good. Always in range 0 to 4 for comparability. Actual. What? This would be a cool paper to read. But I'm getting distracted. All right. What were we doing? Yeah, how does protein NMR work? Strong magnetic field to behave like tiny magnets. The sample is probed with radio waves, which excite these nuclei. The frequencies at which the nuclei absorbs and emit energy are measured. These frequencies influence. Yeah, all right. Fair enough. Purified protein is strong at causing the atomic nuclei, hydrogen, to behave like tiny magnets. The sample is then probed with radio waves, which excite these nuclei. The frequencies at which the nuclei absorb and emit energy are measured, and these frequencies are influenced by the chemical environment and are recorded as a spectrum. Cool. All right. So if they ask me about any of these, then I kind of know. But really, I'm kind of emphasizing here the limitations of each of these techniques. So X-ray crystallography is hard to do because crystallizing a protein is not trivial. And also they exist in like a non-native conformation because of crystallographic effects. Cryo-EM is expensive. You have to go to like a specialized facility and get special training. And also you could argue that really a lot of the conformations that you observe are kind of non-native because they're literally frozen. And then we have protein NMR, which is great, but it requires high protein concentrations, and you can't really do like large proteins. So with all these limitations in mind, I want to present the case that HDX-MS actually addresses most of these limitations. For one, there's no size constraints. When you study the protein using HDX-MS, the proteins are in their native conditions. It's inexpensive and then pretty easy to do. And you actually have time-resolved dynamics as well. So potentially HDXMS is as close to native as you can get, I would argue. But like anything else, this has drawbacks as well, which the main ones are the poor resolution. So this is kind of like a deal breaker for many people because HDXMS only can measure on the scale of peptides rather than like atoms or per residue. There's also like interpretability. So there are actually like many reasons why, say like, so should I like, am I kind of getting ahead of myself here? I guess not. I mean, I should at least address that though. What I'm saying is like I'm introducing HDXMS without really like telling them what it is, which like I will here, but all right. So can they ask me any questions around this? And they could ask me like why. I could answer all of these really. Like why is cryo-EM expensive? Maybe. So let's look that up. Why is cryo-EM due to the high cost of the high-resolution microscopes, which require expensive components like field emission guns and direct electron detectors. Need for sample preparation, data collection, and processing also contribute to the overall expense. Let's look at shopping. So you need expert staff in maintenance, training, processing the vast amount of raw data into high 3D models, computationally intensive, software, data storage. But this is kind of like the output you get from like a cryo-EM prediction. So I would say high cost of high resolution microscopes. Wow. For example, a Titan Kronos microscope costs up to 6 million. This guy's happy. Y'all give me enough bits so I can afford one of these. Yeah, so specialized staff. Data computationally expensive to analyze data. All right. So then with protein NMR, why do you need high concentrations of proteins? Because it relies on detecting weak nuclear magnetic resonance signals from a relatively small number of nuclei within the solution. Okay. That's cool. I mean, micromolar, like, is that hard to get sometimes? So why do you need high concentrations? Because it relies on detecting weak nuclear magnetic resonance signals. Okay. Size constraints. Larger molecules tumble more slowly and have shorter NMR relaxation times, which causes the signals to decay and broaden too quickly. Interesting. The signal to noise ratio decreases as size increases, and the complexity of the spectra for larger proteins make them difficult to interpret. So, tumble more slowly and have shorter NMR relaxation times, which causes the signals to decay and broaden too quickly from us. Man, what is tumbling? As the tumbling rate or correlation time impacts the signal sensitivity result. Fast tumbling tends to longer. So this comes down to like how NMR works, really, I think. This is cool though. Yeah, diving into like protein NMR would be pretty interesting. Yeah, you'd learn a lot there. It'd be hard though, but I think it's a worthwhile endeavor. Maybe one day. Start a model for protein NMR. All right. Protein tumbling in solution is crucial for high resolution, as tumbling rate or correlation time impacts signals. Fast tumbling, typical for smaller proteins, leads to longer T1 longitudinal and shorter T2 transverse relaxations. So what is that? Like, why does fast tumbling because it's less efficient at transferring energy to the lattice surroundings, but it shortens T2 because the rapid motion causes greater dephasing of spins. Oh God. Yeah, see, this is getting into the weeds now. I remember learning about this. I understood it like once, and then I kind of forgot what was going on. So, we're not going down that road hole. That'll be one of those questions where, like, I'll say, I don't know, bro. So, like, you need high protein concentrations because they're basically weak NMR signals. So the more protein concentrations you have, the greater the signal to noise ratio is. And then you can't do larger proteins because um, the complexity of the graph, well, what would we call it? The complexity of the readouts would just increase. So that's one problem. Another thing has something to do with like the tumbling of like different sizes of proteins, and it affects the broadening of NMR signals. Don't ask me to explain that. That's what I'm going to say. All right, so we answered those questions. All right, so right here we're arguing that HDXMS is a better alternative for each of these for getting dynamical information. There's no size constraints. Why is there no size constraints? Because the readouts come from the chopped protein from it wouldn't be ligation. It'd be what's the word for it? Proteolysis, right? So you could do that for any size protein, basically. It's called proteolysis, right? Yeah. They're in their native conditions because basically the only thing you're changing about the conditions is D2O, right? Which kind of acts functionally the same to like water, you know. It's inexpensive because all you need is like a typical MS setup for the most part, and you need to buy heavy water. And then it gives you time resolved dynamics, which other Um, Other experimental readouts only give you like a scalar value for dynamics, right? But the drawback is, and this is kind of like what's the deal breaker for a lot of people, is that it has poor resolution. So, as I mentioned earlier, the readouts come from proteolysis, which is like basically a small section of the protein. So you can't get to like residue level interpretability and or residue level readouts. But also, those readouts that you do get are subject to a lot of different factors. So it's an interplay basically between like solvent channels, auxiliary motions, temporary disordering. So the chemistry that governs exchange is pretty poorly understood at this moment. But I'd still argue that like the next frontier in this discipline in general is predicting the motion of proteins. So right now AlphaFold can predict the structure, and we need to start moving towards predicting motion. So given what HDX-MS offers, I'm placing my bet in this technique, giving us the data sets required to train these next generation models. The data is easy to collect, it's cheap to get, there's no size constraints, and the proteins are as close in their native form as really possible, I think. So let's talk about like what is HDX-MS. All right, are there any other questions here? I don't think so. A lot of these questions over here will be addressed, right? Upcoming slides. All right. So we're 2 hours in and we're on slide 19. That's great. This is taking infinity long. I can't sign in this way. That's so odd. I think something's happening. All right, so here's an overview of what HDX-MS is. So the way you begin is by taking your protein with whatever state you're interested in. So in this case, it would be horse heart cytochrome C with heme bound. And you would first dissolve that in D2O. And at that moment, an exchange reaction begins to occur where deuterium replaces hydrogens at the peptide bond. So here we're showing the base catalyzed mechanism of this process, which is normally how this exchange process takes place. So the question here would be, what is the acid catalyzed mechanism for D2O? I probably need to know that. I'm not reading a paper from the 60s. I could probably reason my way through it. There was a paper somewhere. Um, I'm hungry. I can make a smoothie real fast. Overleaf. So I'll try to find the source here. I think it was around maybe here. Hydrogen, deuterium. Fundamentals of HCXMS. Does it give us a mechanism? I don't know where that paper was. Acid. Just looked at that. Maybe here. Oh, this might have been it. No. I mean, this is the base catalyzed mechanism right here. No. Oh, here we go. Okay, this would be this. So the acid catalyzed scheme would first start with the resonance structure, then the protonation of the carbonyl, and then D2O would pick up that hydrogen, then add it back to here. So that's one scheme. Or it could be like that. And there's the base catalyzed. All right, so we're wondering why would one be favored over the other? Proton transfer theory highly sensitive to exchange reaction conditions with a local electronic environment. Here we'll attempt to distill the core concepts underlying this relationships. Hydrogen exchange process. It's the side chain. Okay. 3 mechanism: acid, base, and water catalysis. Okay. So these are 2 separate things. So which one's water catalysis? Acid catalysis. Oh no. Maybe not. You ever got any song racks? You want music playing in the background? Alright. One describes the O-protonation acidic emitic exchange. Acid-emitic exchange, which is understood to be the predominant pathway of acid catalysts for backbone amides. Okay. The emitic nitrogen is then this process begins with the transfer of deuterium from the solvent to the peptide carboxyl oxygen. Right here. The emitic nitrogen is then deprotonated, which is followed by the transfer of deuterium from the solvent back to the nitrogen. Okay, it's just talking about this whole second path. Scheme 2 displays the path for N-protonation for direct deuterium. This pathway begins, it should be noted that the N-protonation pathway is not primary exchange, with the possible exception being the N-terminal. Okay. How did I know that? I guess from here. Charles. There's the DUI. Okay, that doesn't work. But why can't I read it? Oh. Alright, whatever. I guess I'll never know. The process of the base catalyzed amide exchange, on the other hand, is understood to be through a single pathway. Base catalysis begins with the direct removal of hydrogen and the resulting highly basic nitrogen. See, this makes sense to me. That's why I did the base catalyzed mechanism. Also, it's shorter, so that's why I wrote it right here. Then unionized form is also capable of initiating, albeit at a much slower rate. Deuterium oxide is then unionized form. Because of the tendency of ammo exchange to proceed primarily through base. Okay. Furthermore, because of the tendency of amide exchange to proceed primarily through base catalysis above pH 2.3 or 2.6, is observed is considered minimal. It's like the pKa of like this amide bond here is probably around 10. Let's ask Jeopardy. The rate of exchange is unique to each amino acid type. Yeah, that's because sidechain chemistry. Yeah. Okay. So they might ask me a bunch of shit here on like the mechanisms for exchange. So this is, I kind of need to deep dive a little bit. So I guess I'm just going to give this to ChatGPT real fast. Read the following paper and explain the acid base catalysis of deuterium exchange. Why is the base catalysis? I'll just say which is favored and why. Here is the paper. What? Damn, how many citations are there? I didn't realize that. Oh, there's like 1,000. Okay, they literally wrote a book. Alright, scratch that. Blank paper and explain what? Explain the acid plus basic catalysis for exchange, and why one is favored over the other. Here is so what we got going on. So I could read this whole thing, but this might take me like a day. Why can't I scroll? So pH affects logs PHT. All right, please run in like a reasonable amount of time. I don't know why CPP Traj is so slow. Looks like it's not. Yeah, it's gonna take forever. All right. Yeah, it's really thinking on this one. Controlling solution pH is fundamental to HDXMS experiment. In fact, the sensitivity is what enables the retention of deuterium for analysis by MS. Proteins are typically labeled around neutral pH or under near physiological conditions. The pH range is relatively fast, enabling probing of diverse protein motions on a reasonable timescale. To actually observe the localization of deuterium and gain any structural insights from it, it is necessary to slow the exchange quench reaction. Otherwise, process of HTO and subsequent sampling handling will result in the loss of deuterium label. Although the quench step serves additional purposes, the slowing of amide exchange is accomplished here by acidifying the exchange reaction buffer to a range which rates of acid and base catalysis are minimized. The negative sloping region on the left side of the plot represents the region where amide exchange proceeds primarily through acid catalysis. corresponding positive sloping region in the right resistance. Interesting. Okay. So why is it quenched with acid? Maybe it'll tell us that. 3-step catalysis and D2. Water term. So slow it's usually ignored in solution. Key story, at low pH, the acid term dominates. At physiological pH, the base term dominates, and around both are minimized for quenching. Yeah, that's what we just read. Emitic pathway. Okay. It's good to know. Why is this the main acid pathway? Because electronically the cation is less stabilized, yeah. Base catalyzed is simpler and is what matters near physiological conditions. Rate limiting is the NH bond cleavage by OD. Anything that stabilizes the developing neutron speeds this up. That's why there's a strong sequence of nearest neighbor effects. Okay, so that's good to know too. Why base catalyzed dominance of physiological? Looking again, 2 key factors. HDX is base catalyzed. Consequence, raising pH by 1 unit near neutrality. Tenfold. Okay. So I think here is where we should probably have some extra slides start coming into place. So I want to include this probably. Oh. We'll just do desktop, I guess. Does that work? Nope. Oh. Here. We can move that to trash. There we go. All right. So we had another question, I thought. Okay, so I think the question is like, I get why it's mostly the base catalyzed mechanism, because there simply isn't a lot of OD3 around in solution. But like at around like a pKa of 10, the peptide bond would probably be half and half in its protonated and deprotonated form. So at around physiological pH, it's mostly protonated. Okay, so this is just talking about like the way it happens, I guess, not necessarily how frequently it happens on the amide bond. So this is fine. All right, so let's get into this. What is the acid catalyzed mechanism? So there's two possible pathways. With the main one being the emitic pathway. So D2O transfers to the carbonyl. How do I put this in like one sentence? I need some food. I think I'm going to take a break, get some food, and then open stream back up again. So I'll be right back.